Hey, I've got two jokes to start off the day for you. They're based on trigonometry. So here we go. Joke one. I got a sunburn on the beach yesterday while I was reading about trigonometry. You should see my tan lines today. Get it? Tangent, tan lines. All right, here's number two. Maybe this one will make you laugh. My boyfriend has a trigonometry fetish. Every time we talk, he gets off on a tangent. Ha ha ha. Tangent is just such the topic of trig jokes. Gotta love nerdy math teachers. All right, so hopefully you have your note sheet printed off. We are going to look at 721 today, and then tomorrow we're going to do a practice worksheet, very similar to the lessons 2 and 3 that we did with 717. So go ahead and follow along with me. We're going to be doing some graphing today, so bear with me as I do it on my iPad, and we'll just see how it goes. So, it says in Chapter 2, we developed expertise in investigating functions and transforming parent graphs. Remember those parent graphs were like x squared, x cubed, absolute value of x, cube root of x, square root of x. In this section, you will investigate families of trigonometric functions and their transformations. By the end of this section, you will be able to graph any sine or cosine equation and write the equation of any sine or cosine graph. But realistically, we are focusing on sine today and tomorrow. Okay, so in section or question 113, it says, we have seen many functions in this course. X is generally used to represent an input, and Y is used to represent an output. By this convention, trig functions should be written as Y equals sine X, and Y equals cosine X, Y equals tan X. But beware, something funny is happening. So we are going to look at graphs A, B, C, and D. And we are going to think about what really does the X and the Y represent on each of these graphs. So if we look at letter A, okay, letter A is really the unit circle. Okay. So we need to think about on the unit circle, we talk about X values and we talk about Y values. But in reality, what does X represent on the unit circle and what does Y represent? Okay, well, we have kind of memorized that X represents the cosine of whatever reference angle or angle that you're focusing on. So if we are looking at this point right here. Now remember, unit circle, we're always talking about points on the circle. Okay, our angle is really right here, but when we talk about the value of X and Y, it's going to talk about the cosine of the angle, which is really the position along the x-axis, and then Y is going to talk about the sine of the angle, which is the position on vertically. Okay, now when we look at letter B, okay, we see a periodic wave, something that is repeating over and over again. Now I know we have definitely slept since we saw this graph, but before break, if you go back in your notes, we graphed something from 0 to 2 pi that looked like this S shape. Okay, if you recall, this is the graph of Y equals sine X. Okay, but we've got to be careful about really what's going on here. So what is our input? Our X values are the angle measures on the unit circle. Okay, now I'm not going to make tick marks for all those angle measures, but we have to know that X represents the given angle that we are really caring about. So a lot of times we won't use X, we will use theta. Okay, but then what is Y going to represent? Okay, Y is going to represent the height of the given angle. Okay, which again, we're going to call that the sine of theta, which sine is all about vertical motion. So that is the height of the angle. Okay, so you need to memorize that this S shape is indeed representative of the parent graph y equals sine x. Okay, now you might be looking at part C and thinking to yourself at first, that's the same exact graph, but it's really not. If you look at the period from 0 to 2 pi again, what is the shape? Okay, the shape is kind of this valley, this U shape. And we actually did create this graph before spring break. And as a reminder, this graph has the equation y equals cosine x. Now we said kind of if you look at always starting on that axis, you can see kind of if you turn your screen a C shape. So the valley forms a C shape, which represents cosine. Well, again, what does x represent? X represents the input or the angle that we are focusing on. So maybe we're focusing on the angle pi, which is 180 degrees. So at this point, then when we look on the graph underneath pi, what is that value giving us? What does -1 mean? That is actually giving us the cosine of the angle, which is really representative of kind of the base or the horizontal distance of the angle, if we're thinking in terms of the unit circle. Okay, so you always have to be visualizing this unit circle when you're thinking about sine, cosine, and then also this new graph that we've never seen before, which is called the tangent graph. So I'm not going to dive too deep into this tangent graph, but you do have to be able to look and see, okay, that this is the graph y equals tan x. So you need to kind of memorize this. Now, what makes it unique from sine and cosine? These asymptotes right here. And if you recall from lesson 717, okay, sometimes the tangent was undefined. If you look back at your worksheet, okay, the tangent of pi over 2 is indeed undefined. And you can see that there is an asymptote at pi over 2, which is right here, okay? So in this case, once again, x is going to represent the angle I just talked about, pi over 2, so that's like an example of an angle. And then y, the output, the vertical value on the graph, is going to represent the tangent, which is really the slope of the radius in the unit circle. So the slope of the angle. But again, what is representative of the slope of the angle? We came to the conclusion that that was tangent, which remember tangent is sine, sorry, I'm getting really small here, over cosine. So keep that in mind, okay? So you need to be able to just look at these parent graphs and recognize that we have sine, we have cosine, and we have tangent. Those three graphs. Now, for the rest of the lesson, we're going to kind of zoom in and zero in on the sine. Okay, so we are going to apply our knowledge of transforming graphs. So we're thinking about shifting left, right, up, down, stretching, as well as reflecting. And we are going to do that to one cycle of the sine of x. Okay, so it says that we need to sketch a graph of one cycle. We call that one period, okay, of the sine of x. So if we're thinking about the cycle of a normal unit circle, okay, we need to think about, okay, how many radians is one lap around? It's 2 pi. So you always have to start and define what is the cycle. Okay, so if I'm making my graph, trig graphs are kind of different because you're going to want to make them a little longer because we're focusing on traveling around the unit circle. Now, if we're thinking about sine, okay, we know that we have 2 pi And we really want to take advantage of those axes where the sine or cosine are 0 and 1. That's way easier to graph. So we know that we're not going to go above 1 and we're not going to go below -1. And we see that we're definitely going to take advantage of pi. And then what are those y-axis marks? We're going to have pi over 2, and we're going to have 3 pi over 2. So now, if I go ahead and maybe make my pen a little thicker, we're going to think about the values of these angles. So if we go to 0 on our unit circle, what is the sine of 0 radians? The sine is 0 because we do not go up, and we do not, so that's 0. Sorry, I'm distracting myself with trying to make this graph look pretty. Okay, so then when we go to pi over 2, what is the sine of pi over 2? Which is right here. The sine of pi over 2 is 1. So I'm going to put my peak there. And then what is the sine of pi? That is 0 because we didn't go up any. And then what is the sine of 3 pi over 2? That is -1. And then the sine of pi over 2, we are back to not going up or down at all. So we've memorized that the parent function for sine, okay, looks something like this, and you can see that when we connect those dots, that is exactly what it is. Okay, so we can see that, let's go ahead and just color code. It says label the x-intercepts. What are our x-intercepts? It's 0, 0, pi 0, and 2 pi 0. And then what are the maximums? The maximum point is right here. So it would be pi over 2 comma 1, if we want to write that in. Pi over 2 comma 1. Okay, because our input is the angle, our output is the sine value. And then what is the minimum? The minimum is right here. So it's 3 pi over 2 comma 1. Okay, we're not on the unit circle anymore. So our input is the angle. The output is the sine value. Okay, so that's the minimum and that is the maximum. Okay, so from here then, we are going to now transform this parent graph. Okay, so if you want to make a note that this is indeed the parent function that we are going to be working off of quite a bit. Parent function. Okay, so let me zoom in, see what we're doing here. We are going to sketch the following graphs of y equals sine x using 5 points. Okay, but what we are going to do is we are going to work on translating at the same time. So we know our 5 points from what we just did, and now we are going to focus on translating 2 units down. Okay, so if we go ahead and get thinking about those key points, we normally would start at 0, 0 because the sine of 0 is 0. But we are now going to shift 2 units down and put a point at -2. Okay, so then we're thinking about when we get to pi over 2, okay, normally what would we be at? We would be at 1 because the sine of pi over 2 is 1, but if we shift that point down, okay, 2 units. Then at pi, we would normally be back at 0, but we have to shift that down 2. Then at 3 pi over 2, we would normally be at -1, the bottom of the unit circle. But then if we shift down 2, we're actually going to be at -3. And then finally at 2 pi, we're back to 0, but we've got to shift that down 2. So if we go ahead and connect our dots, we can see that here is the transformed function. Now, I should have probably before this drawn out the parent function. So let's go ahead and draw that. You're going to get fast at doing this. 0, 0, pi over 2 is 1, pi is 0, 3 pi over 2 is -1, and then we're back to 0. So if you look, this is the parent function, and then the red function is our new function. Now, what is the equation of the red function going to be? Okay, well, if you think back to our transformations unit, we have y equals sine of x, but then what did we do? We shifted down 2. So that -2 is tacked on at the end because it's a vertical shift. Okay. So now let's try a different one, and we're going to start again with y equals sine x. So try to do that on your own. Plot your points. Make your parent function. Okay, and then from here, let's look at doing this in the negative direction as well, because I ignored that on the last problem. Okay, so if we think about continuing the pattern on, okay, the sine of negative pi over 2, you saw that video yesterday, is going to be the same thing as the sine of pi over 2, but just with that negative, and then we're going to continue the pattern to make what we call an oscillating sine wave. Okay, and you can just see how it goes up, then down, then up, then down, and so we can add arrows on to show the repetition. Now what we want to do is we want to vertically stretch by a factor of 4. So what does that mean that we're going to do to all these points? We are going to multiply the y value by 4. So instead of going up 1, we're now going to go up 4. Okay? But we are stretching, so we're not shifting. We're doing that in every direction. But it's important to see that what is 0 times 4? 0 times 4 still remains 0. So all of our x-intercepts will remain unchanged. That's kind of the key with vertical stretches and compressions. So if I get a different color, okay, we are going to start at 0, and again, my 0 stays the same. But then when I get to pi over 2, I have to take 1 times 4, and now I get to 4 on the y direction, and then I get to pi, and the sign is 0, so 0 times 4 is still 0, but then 3 pi over 2, when I multiply -1 by 4, I get -4, and then I'm back to 1, and I can continue that pattern in the backwards direction to make it look nice and pretty. And then we can go ahead and look at what a vertical stretch, one second, what a vertical stretch is going to look like. Okay, so what is the equation going to be for this? Okay, the equation is going to be y equals 4, that's like our a value out front, times the sine of x. So hopefully you're kind of recalling slowly but surely those transformations. Vertical stretch and compress is going to be the constant multiplier out front. All right, so now we're going to do some practice problems where we are going to continue to write equations. Now, I would encourage you to put me on pause if you think you're getting the hang of it. Let's continue to put the parent graph so that we can see kind of the difference between the parent graph and the transformed graph. So we are now going to shift up 3 units. So I'm going to go ahead and I am going to make my units. So I have 0, this is my parent graph, so I'm just going up 1, down 1, and then same thing in the reverse direction. And then I can go ahead and connect the dots here. So there is the parent, and then from here I'm going to go ahead and get a new color that what are we doing to these points? We are shifting every point 3 units up. So this shifts, the shifts are easy because you just count 3 units from each point. So 1, 2, 3, and so on. And you can kind of see that when we don't have a vertical stretch or compress, okay, that same shape is taking place, and you can start to envision kind of a new, I'll call it x-axis, where you have this point where those original x-intercepts were, okay, but now it's at the line y equals 3 instead of at y equals 0. Okay, so then from here I can go ahead and connect my dots. And so then what is the equation for this sine wave? This new sine wave is going to be y equals the sine of, I'm going to put x in parentheses because we're going to see something here in a little bit, but what did we do? We shifted it up 3 units. So that is our equation. Now is where the horizontal shift comes into play. Okay, so now you're going to notice that shifts in trigonometric functions are oftentimes used in terms of pi rather than solid whole numbers. So I'm going to go ahead and quickly put my sine function on the graph. You do the same. Okay, so there is our parent function, but then now we want to go ahead and look at shifting pi over 2 units to the right. Okay, so we're going in this direction. So I'm going to take every point and literally just move it pi over 2 units. Now when you have a scale, it's not that bad. So really, I'm shifting 90 degrees. Okay, so I'm going to look at my origin point, and I'm going to move the point over to pi over 2. Now the peak of my mountain is going to move to hover over pi. Okay, and then I'm going to shift my original pi over to pi over 3, and then I'm going to shift my pi over 3 over to 2 pi. Okay, and then I'm going to do the same thing. If I start back at negative 2 pi, that point is going to go to negative 3 pi over 2, but then the peak of the mountain is going to go over to negative pi. And then negative pi will become the x-intercept at negative pi over 2. And then the bottom of the valley is going to shift over to being my y-intercept. So now if we go ahead and look at what is happening, okay, we can see 2 full periods of the sine wave occurring, okay, but you can kind of notice that the peaks and the valleys and the x-intercepts, everything is shifted over pi over 2. So you can maybe guess what the equation is going to look like when we deal with horizontal shifts. Let's write it out. We have y equals the sine. Now when we shift right, remember, that is subtraction, which is kind of against our gut instinct. So x minus pi over 2. And you need to put that all in parentheses. So notice the difference between your horizontal shift versus your vertical shift. The plus 3 was outside of the parentheses of x, and then the pi over 2 was in paired with x. Again, pause me if this is easy for you, complete the problems, but I'm going to keep going. So let's go ahead and get our normal function going on. I should call it a parent function, not a normal function. Now what are we doing? We are reflecting over the x-axis. So I like this one because guess what? We don't have to worry about those x-intercepts anymore. Or again, we don't have to worry about those. What are we going to do? We are going to reflect the peak of the mountain is going to become the valley. Okay, so we still have our x-intercepts as the same thing, and then valley becomes the peak of the mountain. X-intercept stays the same. Then the peak becomes the valley. X-intercept. Valley becomes the peak. And then we have an x-intercept. So reflections aren't too terrible because you get to literally just focus on the peaks and valleys. So do you remember what happens when we reflect over the x-axis? We still have y equals, but then we have negative out front of our function. So negative sine of, and I'm always just going to get in the habit of using parentheses in case I have a horizontal or a vertical shift. We have one more problem to practice. We have a vertical stretch by a factor of 2. So let's put our parent function in there. Told you you'd get fast at this. But I really like to use the parent function because then you can see what the heck is really going on. Okay, now can we guess what the equation for the vertical stretch is going to be? Okay, we're not shifting it up 2, we're stretching it, so it's only going to affect the peaks and the valleys. So we have 2 times the sine of x is going to be our equation. So now we're going to take every peak and we're just going to double the distance. Every valley, we're doubling the distance. Every peak, doubling. So, and then in this case, because we have our peak and our valley are just one unit, the multiplication is very easy, okay? So the height of the wave is going to stretch by 2, but then our x-intercepts are the same. So we can go ahead and see that it just becomes taller and deeper, okay? So that is a stretch. So the moral of the story, the moral of this lesson is which points are the most important to label in a periodic function. Okay, periodic means that it repeats the same pattern over and over and over again. Okay, well, hopefully you can write some of your thoughts down that some of the most important are going to be the x-intercepts. I don't know why it just did that. The x-intercepts, that is when y equals 0. And then what else is important? The other things that are important would be the minimums. What have I been calling the minimums? I've been calling those the valleys, which are the bottom of the unit circle. And then the other thing that is important is the opposite, which is the maximums. Which I'm going to call the peaks. Okay, why is this important? Because we understand the general shape. We understand the general parent function. Okay, so things that we have to consider is we have to consider maybe where is the midline? How long is the period or the repetition of the pattern? And then also, what is the amplitude? Now, amplitude is controlled by the stretch factor. Okay, so the amplitude on number 4 here, the amplitude was 2. Okay, normally our amplitude is just plain old 1. Now, what I want to go back and do is look at the midlines real quick. The midline of, let's see here, let's look at number 1. What was the midline after we shifted? The midline of this function is going to be where those original x-intercepts were. Okay, so I'm kind of graphing that, and what is the equation here? Y equals 3 would be the midline. Just kind of getting you used to some terminology that we're going to continue to see. Okay. The final question of our notes, thanks for hanging in there, you're doing great, is we want to write a general equation when we are utilizing the parent graph y equals sine x. So if you recall, okay, let's just refresh, for a quadratic, the general equation was y equals a times x minus h squared plus k. Okay, where h controlled the horizontal shift, k controlled the vertical shift, a controlled the reflection and the stretch or compress. So, with the parent graph y equals sine x, this is our parent graph, okay, our general function is going to be y equals a times the sine of x minus h, and then plus k. Now recall this, okay, is considered to control the stretch / reflection over that x-axis, okay? The h controls the horizontal shift, and then the k controls that vertical shift. Okay, so in your homework tonight, you might see some practice problems, but definitely in the next lesson, lesson number 5, we are going to do this, and it might even be applying it to the cosine graph as well. Okay, so great job. Keep working hard. Very proud of you, and I will talk to you in the next lesson.